Well, good evening, everybody on Facebook and Twitter. Welcome to the latest of our Bootham talks for this year. The last of our Bootham talks for this year. We've left a really good one to the end of the year. Thank you very much for your patience over the last 10 minutes or so as we've been sorting out the tech in the StreamYard studio. It's brilliant when it works well, but when it doesn't, you know about it, don't you? So thank you so much for waiting during that particular time. But without further ado, it's my enormous pleasure this evening to welcome Jocelyn Burnell. Her connection with Bootham directly, I think, is that her father was an old scholar of the school. I think more importantly to her, she was an old scholar of the Mount, and therefore her connection with Quakers and with York and with education in our city is clearly very important to her. I don't want to say too much about her life and introducing her, simply because that is what she's going to be talking about. And I think she is absolutely the right person to mediate that to you, not to me. Except to say that she is a modest but undoubtedly scintillating star in the firmament of astrophysics and history of astrophysics. And she has discovered some pretty cool stuff. And I'm sure we'll be talking about some of that to us this evening. She's also a Quaker and somebody who has, to my great interest, written on a subject that's quite close to my heart, a subject to which too many people jump to too many conclusions too often, and that is the interface between science and religious belief. So it's my enormous pleasure to welcome to Bootham School and to Bootham Talks this evening, Jocelyn Burnell. Jocelyn, welcome.
Thank you very much. And my apologies for the delays in getting set up. Can you hear me okay?
Absolutely.
And the screen is visible, the first slide?
It will be shortly when you ask for it. Here it comes, yeah.
Right.
Yes, got it.
Good. Thank you very much indeed. So I was going to say a bit about my childhood in York as well as elsewhere, a bit about the discovery of pulsars, which you've had a hint of, and a bit about being a woman in science, particularly a woman of my generation in science. So I started life in Northern Ireland, and the top picture is the school I attended there till I was about 12, initially in what they called the prep department, which was 2 rooms, 2 teachers, and 3 or 4 kids in each year. The secondary school was quite large. I think it was a 2-class entry as far as I can remember. There used to be this exam called the qualifying in Northern Ireland, or the 11 plus, this side of the water. And my academic career started by failing that exam. I think that is in part a reflection of the teaching in the so-called preparatory department. I was allowed into the grammar school stream because it was understood that I was leaving to go to school in York at age 13. So I had my first 2 years of secondary in that school. It was great fun, much bigger than the primary bit, lots of different teachers. You moved from room to room, albeit carrying quite a big pile of books, but I found it very stimulating. But on the Wednesday of the first week of the first term, a message went round the first year class that this afternoon at such and such a time, the boys were to go to this room and the girls were to go to that room. And I thought, Wednesday afternoon, this is sport. That's why they're separating us. But it wasn't. They sent the boys to the science lab and the girls to the cookery room. No choice. Everybody knew that girls were only going to get married, that they needed to learn how to cook and sew and make beds and things like that. And it took apparently about 5 years to teach us. I had wanted to do science. My family had promised me I'd get to do science, but the domestic science teacher wasn't hearing anything of it. When I told my parents that night, they hit the roof and phoned the head teacher, as did the local doctor who had a daughter in my class, and as did one other set of parents. The next time the science class met, there were 3 girls and all the boys. I think that was the first time that teacher had ever taught girls. Clearly we were dynamite. He made us sit right up against his desk, right at the front, so we couldn't cause trouble. We did physics that first term. I loved it. I came top in the exam, getting 97%. For anybody in the audience interested in physics or doing physics, even if they're not interested, here's a tip. One of the questions was, what's the speed of light? And I wrote it down, and I wrote it down correctly first time. And then for the first time, I stopped and I looked at that number. And I thought, that's very big. And changed per second to per hour. And so only got 97% on that physics exam. It is a very good idea to look at your answer when you're doing physics sums. Ask yourself, is that a sensible answer? Is it plausible? But just don't do it for the first time in the exam, folks. That's not such a good idea. I don't remember the physics teacher congratulating me. I do remember him berating the boys for allowing a girl to beat them. We did chemistry the next term. That was okay. Not as good as physics, but it was okay. And in the summer term, we did biology, or what passed for biology. We were given flowers to draw. Draw the flowers, label the parts, learn the names. You've done that? Right. Here's a different flower. Draw the flower, label the parts, learn the names. That went on the whole term. And I decided this was boring and biology wasn't for me. On the whole, I did pretty well those 2 years and then went off to York to boarding school. Quite a big change from Northern Ireland, I have to say, coming to England, but I settled in due course, and maybe some of you will recognise the lower photograph on this slide. I continued good at physics, good at maths. I was also good at Latin. When it came to choice of A-levels, the Latin teacher wanted me to do Latin, but I wanted to do maths and physics. So I did maths and physics. Then I went to university to read a physics degree. I had decided sometime during my time in York that okay, I'm going to do a physics degree, probably at university. What am I going to do afterwards? What kind of physics? Because you can do many, many things with a physics degree. And I finally decided on astronomy, in particular radio astronomy. So I went to Glasgow to get a degree in physics, judging that that was the best qualification for carrying on as a radio astronomer. So the image at the top is Glasgow University, the old building, standing prominently on the top of a hill. I ended up the only female in the honours physics class for the last 2 years. I was living in a women's hall of residence and all the other women were horrified. Oh, you'll change subject, Jocelyn, won't you? That hadn't actually occurred to me, and I didn't. But I was the only female, and there's always a bit of a gulf between the male and the female students, and I didn't have any buddies to work with. I was working on my own the whole way through. I got a reasonable degree, still wanted to do radio astronomy, didn't seem to be getting into Jodrell Bank to do a research for a doctorate, didn't think I'd get into Cambridge, didn't think I was that calibre. Reckoned I was probably heading to Australia, but I put an application into Cambridge just in case. And very much to my surprise, I got a place. Now, in Oxford and Cambridge, as well as being a member of the university, you belong to a college. And this is a photograph of my college, which is called Murray Edwards. It's still an all-women's college. There aren't many single-sex colleges left, but there are a number of women whose families will not let them study in a mixed environment. And so places like Newhall, Murray Edwards cater for them. PhD is a 3-year program, typically 2.5 years of work, and then a frantic year writing what is a very large project report. It's a book, in fact. This is the classic picture of Cambridge. Do you see the punt in the foreground and somebody standing at the back poling the punt along? And in the background is King's College Chapel, which is quite a famous building. Now, a map of the UK. This is really for foreigners. I don't think you'll need it, but you can see number 1, where I started. Number 2 is York, where I had my secondary education. Number 3 is Glasgow, where I did my bachelor's degree. They're all in the north and west of the country, the more mountainous parts of the country. And then very much to my surprise, I find myself down south at number 4 at Cambridge. As seen from Cambridge, there is a distinct gradient in the country. Folk down south reckon they are the ultimate civilization, and this comes to you from quite far south, and they perceive the folk up north, and that probably includes York, as uncouth savages. Well, I'm overstating the case slightly, but only marginally. And when I got to Cambridge, I encountered this attitude. I also became acutely aware that at that time there were very few women in Cambridge, and particularly very few women doing research degrees. And I really felt an outsider, a seriously outsider. And I reckon they'd probably made a mistake admitting me. This is something else you'll need to know about at some point in your life. It's called imposter syndrome. And it's what I experienced when I got to Cambridge. And it goes something like this. Everybody here's very clever. I'm not that clever. They've made a mistake admitting me. They're going to discover their mistake sooner or later, and they're going to throw me out. And in a bad case of imposter syndrome, the student goes on, I'd better leave before they throw me out. And if we're not careful in both Oxford, where I now am, and Cambridge, the students taking themselves off home within the first week, simply because they're scared. Here's how you handle it if you ever feel like that. I'd had quite a battle to get where I had got. I wasn't going to walk out of my own accord. I reckon they would throw me out at some point, but until they threw me out, I was going to work my very hardest so that when they threw me out, I wouldn't have a guilty conscience. And that was my policy, fully expecting to be thrown out, but working really hard until that point so that I'd know I'd made the best of the opportunity. Now, you may have seen a picture a bit like this. It's called the electromagnetic spectrum, or informally, the family of light. And here is light, here is the rainbow. Light spread into its different wavelengths or at different frequencies. And you probably know red, orange, yellow, green, blue, indigo, violet. The red end is the longer wavelength. And if we go out of the red end of the spectrum, we don't see anything, but there are waves there. They're called infrared. Like you get in infrared lamps, infrared heaters. If we go longer still, we come to millimeter wavelength radiation. Things that we have in radar and microwave ovens and microwave links. And if we keep going to even longer wavelengths, we go through the television band, the VHF band, the shortwave band, and the longwave band. And all this is called radio. Go back to the spectrum and go out the other side. So from blue to violet to ultraviolet, It's ultraviolet that causes sunburn. Fluorescent lamps have ultraviolet in them. Keep going, shorter and shorter wavelength, we come to X-rays. Perhaps some of you have had X-rays at hospital. You've maybe had a suspected broken bone or something. And keep going, we come to gamma rays. Gamma rays are used in some radiation treatments for cancer. They're also used to sterilize equipment. This is the only bit that our eyes can pick up, but all the rest of this exists, and we do astronomy from about here, no, slightly higher than that, about there, all the way up and actually way off the end here. So I wanted to be a radio astronomer, so we're working somewhere round about here. And this is what I'm doing in Cambridge. These are some radio telescopes. This one is the British one. This is at Jodrell Bank near Manchester. And it's just been made a UNESCO World Heritage Site. So it has to be kept standing, which is quite a financial commitment. It will be costly because it's old and rusting. But there are other telescopes like it, USA, Germany, and a slightly different style of one in Canada. This is the radio telescope that I helped build and then used. About 6 of us spent 2 years building this. It's huge. It's an area of 57 tennis courts, and there's 200 kilometers of wire and cable in it. And there's like 2,000 TV antennae that make sort of the important part of it. When the construction was done, I was told to get the thing working and get on with my research. I've spent 2 years up to that point, and I've just got 12 months funding left. I got the telescope working. It worked pretty well. Next problem, what to do with the data that comes out of this telescope. At that time, the University of Cambridge had one computer. It had memory comparable to your laptop, and it took up a whole room. It was made with what we used to call valves or vacuum tubes. The transistors weren't really reliable enough at that stage. They came in fairly soon afterwards. And very few people could get time on this little computer. And my supervisor was not one of them. So I didn't use a computer. I had all my data out on chart paper like this. The telescope produced 30 meters of this stuff every day. That's a hell of a lot of paper. We spent 4 days scanning the sky, so 120 meters to scan the sky. And after 6 months, I had over 5 kilometers of this paper. I was looking for a new kind of radio object called a quasar, but I accidentally stumbled over something that's become known as pulsars. Each sky survey would take 120 meters of chart paper. And just occasionally there was 5 millimeters in that 120 meters that showed a signal that I couldn't make sense of. And it wasn't always there. It was probably only there about 15% of the time we looked at that bit of the sky. But I was being so flipping conscientious that when this funny signal cropped up, or after it cropped up a few times, I didn't know what it was, but my brain said, "You've seen something like this before, haven't you? You've seen something like this before from this bit of the sky, haven't you?" And then it's easy, because I file the paper according to which strip of sky we're looking at. So you get out all the other strips for that bit of sky, and you find that, yes, just occasionally this funny signal, whatever it was there. It was only there about 1 in 5 times, but when it was there at the same point of the sky. So it was amounted to about 10 parts in a million, given how short a signal it was and how much chart paper there were. But the human brain is amazing at what it can remember and what it can, so to speak, fish out of the murk. My thesis advisor rightly observed that this only occupies 5 millimeters and we can't really see what's going on. What we need is an enlargement. And with this kind of technology, chart paper being wound under the pen, it's easy to get an enlargement. You just make the paper go faster under the pen and everything gets spread out. The snag is you can't leave it running like that permanently or it gets through the roll of paper in 20 minutes. And Jocelyn would have to live at the observatory putting a fresh roll of paper in every 20 minutes. The next best solution is that Jocelyn goes out to the observatory at this point, switches to a higher speed to spread it out, enlarge it, and switches back to normal at this time. And I did that for probably a month and nothing happened. And then one day, something did happen. These are 1 second time pips. It used to be broadcast in England and we put them on the chart recording. And this is the signal that the telescope picked up. And you can see blip, 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 one missing, blip, 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 blip. 1, 2, 3 missing, faint, faint, faint. And you can see that they're about 1 1/3 seconds apart. We'd seen nothing like this before. My supervisor thought I'd wired the thing up wrong and it was my fault that this funny signal was coming in. But he came out the next day, stood over my shoulder and saw it for himself. And it was immediately a puzzle. Next day, the pulse periods, the spacing between the pulses was the same. So whatever it wasn't getting tired. It was keeping the beat. But it also had to be small because the sides of these pulses are steep. To keep the beat, it's got to have big energy reserves, but it's got to be small and big. Doesn't make sense. It's turned out to be the first detection of a pulsating radio star. Radio because it's radio astronomy, pulsating because it gives pulses. And that's shortened as pulsar. And this is what we think pulsars are now. Here's the pulsar. It is very small. It's only about 10 miles across. It's spinning about an axis, the way the Earth spins, only rather faster. And it's got a magnetic field, like the Earth has, only a hell of a lot stronger. And the magnetic axis is here. And somehow the magnetic field produces a beam that comes out of this cone. So there's a narrow beam that shoots off that way and a narrow beam that shoots off that way. And it's a bit like a lighthouse. If, as it spins around and it sweeps the beams around the sky, if the beam falls on the Earth, we see a flash. And then one rotation later, we see another flash and another after another rotation. Of course, a number of them, the beam doesn't shine on Earth at all, so we don't see them. We probably see about 1 in 10. We now know of about 3,000 of these, and the number is still growing. They are amazing things, even for astronomers. They're very compact because they're only 10 miles across, but they weigh the same as a star. So the pressure at the center of one of these is this number of times the atmospheric pressure here on Earth. I don't know if this audio is going to work. I don't think so. No, okay, never mind. The fastest known pulsar has a period of this number of milliseconds, this number of thousandths of a second. So it's going really, really fast. And if we could listen to it, it would actually sound like a whine. And look how accurately we can measure the period. It's fantastic. And they're very, very stable. They keep going at the same pulse rate, really, because it's quite hard to make a star change its spin rate. Actually, we've now got a slightly faster one, about 1.4 milliseconds. And we'll keep hunting, finding more, and I'm sure that record will change again at some point. We now know of lots of planets round other stars. But 20 years ago, 30 years ago, we didn't know of any around any other stars except for some planets around one particular pulsar. And this is an artist's impression. So this reddish thing is meant to be the radial beam coming out. And then here are some planets going round. And we can see them because they make the pulsar wobble, and it makes the beam wobble a bit on the sky. I can give you several good reasons why there shouldn't be planets around a pulsar, but this one undoubtedly has planets. So that's an interesting puzzle. The roundest known thing in the universe is the orbit of a pulsar, this one, around its companion star. The orbit has a radius of a bit over 500,000 kilometers, and the orbit is circular to 5 millionths of a meter. It's an eccentricity, for those of you who've learned about ellipses and things, an eccentricity of about 10 to the minus 7. And if you go to one of these stars, not recommended, but if you excuse me, if you were to go to one of these stars, stand on the surface and drop something, maybe a coin, the gravity is so strong, the acceleration is so strong, that coin would hit the surface traveling at half the speed of light. So it's gone from 0 to half the speed of light in what, about a meter height. Very strong acceleration due to gravity. Well, all that was more than 50 years ago. And I'll just spend a few minutes talking about what happened next. As I finished that degree in Cambridge, my PhD, the thing that gives me the title doctor, I got married. My husband worked in local government, and the way you get advancement in local government is to move to another locality and go up a notch, go up a grade at the same time. So he moved jobs every 5 or 10 years. He also had a son who was born some years after we were married. And at that time, mothers were not expected to work. It was, quote, proven that if a mother worked, the children would be delinquent. Now, if we were face to face at this point, I would say to you, how many of your mothers work? And I suspect quite a lot of hands would go up. And then I say, how many of you are delinquent? Because if your mother works, the kids are supposed to be delinquent. And there might be somebody in the back row who puts their hand up just for the hell of it. But it's not proven that if mothers work, the children are delinquent. It's definitely not proven. In fact, probably quite the opposite. But that was what was assumed at that time. And other women, I don't know if they were envious or were just trying to make me toe the line, but I remember a new neighbour saying to me, you've got a husband, a new baby and a new house, and you say you're bored. What's wrong with you? Certainly true that previous generations of women did not expect to have careers outside the home, and that subsequent generations do. My generation is about the turning point. So because of all my husband's moves, I started in radio astronomy. The next bit I worked in was gamma ray astronomy. Then my husband moved again, so I moved to X-ray astronomy. Then my husband moved again, so I moved to infrared and millimeter wave astronomy. Then the marriage broke up, and I got a good job and was leading a research group. And rather than being wavelength specialists, frequency specialists, I said, we'll work at whichever of these frequencies will help us understand the stars that we are researching. And I think that's a rather healthy way to go about it. So not only have I worked at all these wavelengths, I've been a researcher, a university lecturer, a tutor, a manager, a professor, a head of department, a dean, a public relations and an outreach person. And it's been a bit varied and a bit scatty, but interesting nonetheless. But a lot of my so-called career was really a succession of jobs. Sometimes those are called portfolio careers. That's a nice way of decorating that. But for me, it felt a bit like snakes and ladders. So we'd land somewhere, I'd find a job, usually a lowly one. I'd work my way up a ladder. Husband would say, it's time we moved to another part of the country. I slid down a snake, had to find another ladder, climbed up that. After a few years, husband said, it's time we moved, went to another part of the country. I had to slide down a snake, find another ladder, and so on. So it did feel a bit like a game of snakes and ladders. But I was fortunate in that I knew what I wanted to do. You do have to be a bit persistent. You also have to take some risks. You usually end up surprising yourself. I was often quite scared at the changes I had to make. But I also learned that one failure doesn't make a disaster. Always aim as high as you can. Try and keep your options open. And sometimes for women, all you can do is laugh because you're a bit constrained if you have husband and family. I've done a lot of storytelling this evening. I think stories are very powerful. For all of us, good management in a place helps. And I think women should not be expected to be we men or she males. I think we should allow women to be women. It's gradually coming, but certainly still in science, it's a bit masculine and the women have to fit in a bit. We desperately need more scientists and engineers. We're failing to make good use of our young women. We know that girls can do physics brilliantly. Don't listen to anybody who tells you girls can't do physics. It's not true. I think girls are more likely to do physics if they're in a single-sex school. And there's data from around the world that shows it's culture, the ambience in the country, not the women's brains, that are the limit. I don't know whether you'd agree with this professor from Harvard, Laurel Thatcher Ulrich, who said, well-behaved women rarely make history. So don't be too well-behaved, ladies, but enjoy yourself. Thank you.
I'm sure that if we were in the hall at Bootham and Jocelyn was talking to us, we would hear deafening applause at this particular point for the talk. And Jocelyn, we're so grateful for those reflections and the just the modesty that you've shown us in terms of explaining your discoveries, explaining your career in the way that you have, and I'm really grateful for that. I want to say to the people who are watching online that if you have a question that you'd like Jocelyn to answer, if you type it in the chat, either on the Facebook or the YouTube page you're viewing at the moment, then a few seconds later, and it does take a little while to come through, those questions will start to appear on our screens. But I think to start with, Mike Shaw, who is our astronomer-in-chief at Bootham School, and has been a long-standing member of staff and has been rightly inordinately excited about this evening's talk in advance, I think may well have a question for Jocelyn that will be far more informed than anything I could try and ask. So over to Mike.
Good evening, Jocelyn. That was a lovely talk. Thank you so much for giving it. I was a bit nervous about calling you Jocelyn, to be honest with you. I think Professor seems to be more appropriate somehow. But a really simple question, and I'm going to put you on the spot here. The girls in our girls' boarding house have been asked to choose inspirational women to name the bedrooms after. And long before this talk came up, your name was chosen. So there is going to be a room named after you in one of our boarding houses. Would you like to think of an inspirational motto that we could stick on the door that would sum it all up?
Whoa. Can't think of anything sort of totally off the cuff, but I'm sure with a bit of thought. You don't want a whole paragraph, do you? You really want just a sentence.
I think so. But if you can think of something, email it to us and we will get it stuck up there.
Right.
Thank you.
Right. Okay.
Maybe something along the lines of "behave badly, girls." You never know. You never know. So please do ask questions. Those of you in the audience, so put them in the chat, and they'll come up on our screen in a minute. Do you think you could sort of reflect for us a little bit, if you're happy to, about how your life as a Quaker and your life as a scientist have interacted with one another. Well, what has been the effect of either on the other, as it were?
One of the things I like about being Quaker is you are not told what to believe. You're actually told to work it out for yourself. I mean, okay, there'll be people you can discuss things with and try out ideas on and so on, but you are not told what to believe. And that suits a scientist extremely well, because a good research scientist has an open mind. You don't go in saying, I am going to prove that, because nature may have other intentions, to be honest. You can try to prove that, but you have to be open to the possibility that what you're trying to prove is actually wrong, and you won't be able to prove it. So having an open mind is very important in science. And I like the way that Quakers encourage you to think quite hard and quite sincerely, but do not dictate. They allow you your open mind. So it suits me very well, Quakerism and research science.
Thank you very much. That's a lovely answer. Got a few questions coming in now from some of the young people. I've got a slightly cheeky one from Finn Taylor, who is in our year 10 at school, who says, how did you feel about the inverse image of your pulsar being used for the album cover of Joy Division's Unknown Pleasures?
Yes, that was the very first pulsar that they took data of. Well, they got data of. It wasn't actually my data, because my data was far too ropey to use on a T-shirt or a sleeve. It was a later observation, but it was the first pulsar discovered. And I thought, that's rather good. And the pulsar does have a great beat, 1 1/3 seconds is quite a good beat for music.
Yeah, lovely answer. Now I've got something from Grace, who is in our lower 6, our college one. And she says, if a planet with life was orbiting a pulsar star, how would that affect life? Would it be possible to have life there? Would it affect the planet at all?
I think it would be dodgy because of the very, very strong magnetic field. Your mobile phone would get wiped, your bank cards would get wiped. And in your body, the positive and negative charges would get separated. So I wouldn't suggest trying it, to be honest.
A similar sort of speculative question from Amira, who's just finished the GCSEs with us, who said, do you think we'll ever find alien life?
There's always some people searching for alien life. I think we've never actually stopped. And I think there is alien life because the universe is so very, very big. Whether we can pick it up, whether we can see it, discover them, I don't know. But I would be very surprised if we were the only intelligence in the universe. And I get less and less surprised. Sorry, that's complicated. I get more and more impressed by the number of planets we are finding around other stars. If you look up at the night sky, not tonight because it's midsummer, but in wintertime, if you look up at the night sky and you'll see several thousand stars, you should say to yourself, there's as many planets up there as there are stars. There's an awful lot of planets in the universe, and we are discovering more and more and more every day. I think the chances are that there is life somewhere, maybe several somewheres in the universe. I think the chances of making contact with them are pretty small, to be honest. So we might never know where they are, but I think they're probably there.
Yes, I would concur with that too. A couple of questions specifically about pulsar. One from Benji, who thanks you for your amazing talk, and then it asks you, what is the most fascinating aspect to you regarding pulsars? But Rachel more prosaically asks, what does cause a pulsar to form in the first place? So what causes a pulsar to form, and what is the most fascinating thing to you about them?
bigger than the sun, things like Betelgeuse, end their life with a very dramatic explosion. And in the explosion, the core of the star gets kicked against, it gets squashed, and it becomes one of these pulsars, which are just about 10 miles across. So we think that's partly why we think there must be a lot of these stars around, because there have been and there will be a steady stream of these exploding stars. When the star gets compressed, its magnetic field and its electric field get compressed as well. The field lines get squashed together, if that'll make sense to some of you, but maybe not all. So the electric and magnetic fields are very strong as well. And that's the recipe for a pulsar, rapidly spinning, strong magnetic field. Now, I've forgotten the second half of the question. Sorry, would you say that again?
What's your favourite thing, your favourite aspect about researching pulsars?
I think what I find most amazing is the extremes. Pulsars are extreme in every possible way. They're extreme in density, extreme in magnetic field, extreme in rotation, extreme in electric field, extreme in gravity. They're inside the star itself. There's a whole lot of very extreme physics all at once. So it's going to keep the physicists busy for quite a while, understanding them.
Lovely. Okay, another one here from Charlie, who says, what are your thoughts on the idea that all of our current scientific theories, this is a big question, all of our current scientific theories probably only describe a small part of what we see out there in the great unknown?
Yeah, and of course the search is on to find other things.
Thank you.
But this might be an allusion to dark matter and dark energy. Cosmologists have recently been forced to admit that all this material that we spend a lifetime studying as physicists only makes up about a quarter of the mass energy of the universe. Another large chunk is what we've labeled dark energy, and the other large chunk is dark matter. And at the moment, we don't know what dark energy or dark matter is. So all our labor up till now has been on 25% of the full stuff of the full universe. And the other 75%, we now know it's there, but we have not a single clue what it is. And there's a lot of very exciting research going on trying to work out what is dark energy and what is dark matter, along with properly understanding the stuff that, we know about, the ordinary stuff, the stuff that we're surrounded with.
If I could jump in, I've got a question here from Maya Lindridge, who has to put up with me for astronomy and biology lessons, so I know exactly how important this is to her. Maya says, as a female in science, what advice would you give to your younger self and to others in today's world?
Yeah. First of all, there are a lot of us working to make things better for females in science. It was really quite lonely when I was a student. There weren't many other women to talk to about your work. Other women weren't interested. And okay, you can talk to the guys, but it's also nice to have some women to talk to. The number of women in science is going up pretty fast. A lot of them are in the biological sciences. Quite a lot are in chemistry. Physics has the smallest number, but is working very hard to get that number up. A huge amount of effort going into that. And a good deal of care now being taken to ensure that women have good treatment, fair treatment, and don't feel isolated.
Thank you. Thank you very much.
Thank you very much indeed. I've got a couple of questions about the dark matter discovery. Dinithy and Naman have actually asked a couple of questions about this. And basically, there's summed up by Naman in his question, which is, do you think that the general theory of relativity first proposed by Einstein has been proven wrong by the recent dark matter distribution map discovery? Big question.
No, I think it would be premature to say Einstein's wrong. Einstein's been remarkably right. I mean, there have been a lot of occasions. This will prove Einstein wrong. It didn't. This will prove Einstein wrong. It didn't. Sooner or later, he might be proved wrong, but we're a hell of a long way off that at the moment. So I wouldn't count on it, certainly in my lifetime. Whether it would be in the lifetime of some of the listeners, I would suspect probably not, but I could be wrong. Yep. We are at the same time notching up a number of questions which may be related or may be unrelated. We don't even know at the moment whether the things we don't understand are all separate things or whether there is some linkage between them. So there's a lot of research to be done, a lot of basic physics to be scrutinized.
Thank you for that. That's great. I mean, I have to say that I was very impressed when I was watching this on the news the other week, and I shouldn't be surprised. I guess I'm not surprised that the scientist who was talking about the fact that his work may have been, his life's work in effect, may have been almost completely undone by this discovery, was actually excited about the fact that that was the case. Do you get that? I'm sure you do.
Yes, I do. Particularly in astronomy, we are discovering new things right, left, and center. So one of the things that was accidentally discovered by pulsar astronomers is that there is something that gives out single pulses. We call them fast radio bursts. They're much, much more distant than the pulsars. The pulsars we know are all in our galaxy. The fast radio bursts come from other galaxies. And it's a very sharp, short burst. Some of them seem to do it once only. Some of them seem, after a while, to do another very sharp, short burst of radio waves. And it's a big, big puzzle at the moment. What on earth, well, not on earth, what in the universe is doing this, is causing this? And particularly the ones that repeat. How is it they haven't self-destructed in producing that first burst? And they're still there to produce another radio burst a year later or several months later or whatever. So total lack of understanding at the moment about what these things are. And at the moment, it's a little bit hard. They're so new, it's a little bit hard to know how to get a grip on them, how to ask a good physics question, because you don't know when the next one's coming and you don't know where it's coming from and you don't know which telescope's going to pick it up, and they won't be ready because they don't know it's coming. Or they could be ready if they sat waiting and doing nothing else, but they don't usually get to do that. So there's a lot going on. I think we're still in a phase where we are uncovering more and more things faster than we are explaining things.
To that effect, one of our listeners, Julia, has asked the question, where do you think work on pulsars will be heading next? Do you have any hopes for what direction it might go in?
Well, one of the very active areas that's going on, and my office mate does this, is studying the inside of a pulsar, which is matter at very, very high densities, and what that actually means when you squash matter that much. Some of it becomes superfluid. Some of it has zero electrical resistance. And in the center of a pulsar, there's all sorts of exotic particles, the likes of which we probably haven't yet seen. So that's interesting. Then there's trying to understand how it produces this beam of radio waves, because it swings a beam of radio waves around the sky. And when the beam shines on the Earth, we see a pulse. So it needs huge electric and magnetic fields to produce this beam of radio waves. And again, it's extremes, right, left, and centre. So plenty of questions and lots of unexpected things turning up. So astrophysics remains, I find, incredibly exciting, with unexpected things turning up every 5 or 10 years.
I've got one here from a student who's obviously very much interested in the future. And Venus Yao has asked, will we be able to use pulsars as a navigation tool if we can travel within the universe in the future? And then she's got a subsidiary question as well. And do you think that we will be able to travel freely in the universe in the future?
Good. Well, pulsars are a bit like lighthouses. They flash in radio waves. Each pulsar has its own flash pattern and its own flash rate. So we could use them as navigation beacons, just like sailors of old used lighthouses. The technical complication at the moment is you'd have to fit something the size of the Jodrell Bank dish to your satellite, and launching that would be difficult. But I guess you could launch bits of the radio telescope, launch the satellite, build the dish up in space and attach it to the satellite. And yes, they can be used like lighthouses. You just have to steer your radio telescope around, say, ha, there's that pulsar. And if you can locate 3 pulsars that you know about, you can pinpoint your position. So they might well be used as navigation beacons, might be done in the X-ray rather than the radio, but the principle is the same. Now, there was a second question that I've...
The second question was a bit more sci-fi, but somebody who wrote LGM on that first trace of a pulsar probably won't mind a sci-fi question. And that was, do you think that we will be able to travel freely in the universe in future? That one was from Venus as well.
Right, thank you. Yes. Yes, we probably could travel quite a lot. Whether you'd really want to issue, you'd be spending an awful lot of your life in a tiny, tiny capsule. So or a fairly small spaceship. I'm not sure that it's something you'd really want to do, but I think we will be able to do it one day, yes. The problems aren't physical, the problems are more on the biological side, How do you keep sane? How do you grow food? How do you do this, that, and the other? Given that you're stuck on a fairly small spaceship, probably for the whole of your lifetime.
Absolutely. Thank you. And we've got one more from Naman Patel. This is an interesting one. In your opinion, which is the most interesting path of study in astronomy? Don't ask more than one astronomer that question.
Yeah, fair point. Indeed. Different astronomers will give you different answers. Some astronomers are very interested in the big picture, the cosmos as a whole, its birth, its evolution. Some astronomers are interested in things like black holes, which we're finding right, left, and center. Some astronomers get very hooked on how a star evolves. So, the sun is a star. What's the future of the sun, for example? It's really what grabs you. I personally am interested in things like pulsars, black holes, gravitational waves, which we haven't talked about. So some of the extreme things like that are what interest me, but I'm not saying that it has to interest everybody. I think, in fact, it's healthy if different people have different interests.
Can I just return to one very final question? And that's back to Finn Taylor again. It's a bit more of a personal question, and in line with some of the terrific advice that you've given us this evening. And that is, when work has got hard and it's felt like you've hit a bit of a brick wall, what has been, if you like, the secret, the drive to help you continue through the difficulties? And I'm sure that's happened many times in your research.
Got more than one task. I mean, even if you're doing research, you're probably in a university, and along with your research, you have duties teaching students. So if the research is a bit sticky, you can put a bit more emphasis on the teaching and get, prepared for next term's course or whatever. And often if you go away and do something else, ideas creep into the back of your mind about how to handle the research problem that you have. So my solution is go do something else. Set it aside for a little bit, let it rest. The back of your brain will continue to work on it. You may not be conscious that it is, but it will be there. And you may suddenly have a realization that, oh, if I look at it this way, it might come out. And so that's the technique I've used, which incidentally means that you don't want a job that is just research. You want a job that contains several different elements so that you can legitimately switch activities if one bit's got a bit sticky and you need some inspiration.
Well, Professor Jocelyn Bell-Burnell, thank you so much for your lecture, to your talk to us. That wasn't a lecture by any means, it was far more friendly than that. Your talk to us this evening. Thank you for mixing up some terrifically accessible science. As a mere historian, I think I grasped almost all of that, which I'm delighted to be able to say. Thank you for mixing that with inspiration. Thank you for mixing that with some really practical advice. Thank you for mixing that all with a sort of sense of modesty and humility that is deeply impressive to me, and I'm sure to those watching. It's been great having you with us, and we wish you all the very best for the future and your continued research. And may you be excited by science and discovery many, many more times throughout the rest of your life, which I hope will be long and productive and thoroughly enjoyable. So thank you ever so much for being with us this evening.
And I'm sorry we didn't get the technology working fully, but we've managed something, which is good.
It was certainly worth the wait. Thank you so much. All the very best to you. And
thank you.
We hope to see you maybe in person one day, and it would be lovely for you to come visit us.
You never know, indeed. Thank you very much.
All the best. Thank you.
Keep safe, everybody.
Thank you. And thank you this evening to Elaine Phillips, whose responsibility it's been to track down the speakers who've been speaking to us over the course of this year. And to persuade them to come and talk to us, and then arranging it all. Thanks to Luke Gilliver, who is our wonderful technician, who enables us to work as smoothly as it does. And thank you to all of you for your attendance this evening and for your commitment to this particular talk. I hope you found it as interesting and as enjoyable, as accessible and inspiring as I have. Good evening to you, and we'll see you again next year from September with another series of talks, which I hope you'll join us for. Thank you.